Good morning, everyone. Today's presentation is about the comparison of different overheating calculation methods in the Belgian context. And I would like to recognize my co-authors, Ramin Rahif and Abdulrahman Fani, who is mainly the master student who worked on this paper, and Mohamed Amer. Well, before starting, I would like to acknowledge Mohamed Hamdy, my colleague who helped to identify and formulate the way that we will use one of the methods for the calculation. I would like also to acknowledge my colleagues at the IEA Annex 80 Resilient Cooling, because this paper is part of their activity and it was inspired by the discussions we are having there. The ULIEGE project occupant that we are working on since 2 years that aims to assess overheating risks and a methodology for calculation of overheating and mitigation measures. Tatiana de Meester, who did previous work on the full monitoring of the building for 5 years with high resolution data. Johan's family, the family of the case study, because they allowed us to get access, and Jean-Marie Augustin, a previous professor who worked on this case also. So the aim of this paper was to investigate the effectiveness of existing overheating risk calculation methods in Belgium. And the first objective was to compare 3 methods for overheating assessment. And there was 2 secondary or less important objectives, which are assessing the overheating risk in the building stock, which I'm not going to talk about today, and formulating a climate change sensitive calculation method. Just to keep you in the condition of the study, the boundary conditions are mainly that we are talking here about the worst possible climate change scenario that can happen in the future in the Belgian context. We have a fixed geometry. We are talking only about 1 case study, and the user behavior regarding opening of windows is a fixed condition, and definitely the thermal characteristics of the building. Well, when we started to review the literature, one of the questions was that we didn't know exactly what is the most common way of assessing overheating, whether on the national context in Belgium or international context. And we figured out that there is a methodology already embedded in the Belgian EPBD calculation method. It's called the overheating indicator. It's developed, I guess, with the initiation of the EPBD in 2008. And we have the Belgian passive house overheating indicator. And just to keep you here attentive to the fact that our Belgian passive house is slightly modified due to the temperate climate of Belgium. So it's not the German, the Deutsche passive house of Darmstadt. And the third indicators that we found in literature appearing as interesting is the ambient warmness degree and the indoor overheating degree indicators, which are developed by Hamdy. And from there, we figured out that those might be the most interesting regarding the regulatory context, the legislative context, and in the same time on the international scientific state of the art. Now, what was the methodology? We are talking here about a lightweight single family construction. It's a nearly zero energy building with a total surface of 174 square meter. It is in Oost-Belgium, which is the east of Belgium, Eupen, in Kettenis municipality. The building is a passive house certified example of sustainable construction. It's advocating for carbon neutrality, not only energy neutrality. And the house is occupied by 2 adults and 2 children. Just to keep you in the context, why we selected this building, because with the carbon tax legislation and what we are seeing with carbon future legislation, for example, in France, sooner or later, we have today in Belgium 20% of newly constructed buildings are timber construction compared to the traditional brick construction in Belgium. And this change, if we project it on a longer period with the carbon taxation scheme that might come from the European Union, we opted for a lightweight construction of timber to foresee what can happen in the future. So this is a kind of OSB construction with fiber cellulose insulation. And it has photovoltaic panels, and it has a solar thermal solar thermal panels for domestic hot water. The building was exposed to pressurization. It passed the passive house requirement. The architect is Leo Michails. And as you can see, the glazing surface is not so high. Unfortunately, there is no external shading system, even though the glazing is not high. And in general, the inertia is not high. Now, following on the methodology, in case you are not aware about the Belgian climate, we are falling in the temperate oceanic climate with no dry season and warm summer. The building is cooling dominated with almost 3,000 heating degree days, and for cooling it's around 100. And the location is latitude 50 north and 6 east. How did we work on this case? We had the reference case, as I mentioned earlier, we had a monitoring of 5 years. This monitoring allowed us to build up our model, and we started to model the building in the EPC tool, which is the regulatory tool that we use for getting permits in Belgium, and in the same time in Design Builder EnergyPlus interface. Then we went through the calibration process based on the ASHRAE Guide 140. Once the model was calibrated and we had a high confidence in the model, we started to run the simulation in the EPBD local tool in Belgium, then do the same exercise in the passive house calculation sheet, the PHPP, and finally run it on Design Builder based on the 2 indicators that were proposed by Hamdy, the IOD and the AWD. So this is simply the methodology, and finally we started to compare the results. So, explaining briefly what are those 3 calculation methods, for me it was very difficult to understand this Belgian calculation method. I tried to get the history from it, but what I understood that so far it was developed in collaboration or based on a German methodology that was developed late 90s. So we adopted this calculation method based on the EN 15251. It's a static or PMV PPD method. And the overheating data is encoded within the energy tree when you start to model the building. And as you can see, the historic data is based from 1958 and 1975. So this is today's regulatory framework that we use to issue any permit. It's a single zone model, and it's quasi-dynamic model, which means that we represent the year 12 times, representing the monthly average. Within our final energy consumption calculation, we have an estimation for need for space cooling, and within this calculation there is a probability calculation for active cooling needs, and there is this probability is related also to the heat gain above the cooling set point of 23. Based on these assumptions, the program will start to run the simulation and calculate the risk of overheating. And once we have these calculations done, our overheating indicator will tolerate a certain amount of hours in Kelvin hours, saying, okay, if it's beyond under this 1,000 Kelvin hours threshold, there is no need to assume that there is an active cooling system. If it exceeds, automatically the software will take into account as if there was a scenario or as if there is an active cooling, and it will penalize the primary energy result at the end in total, which at the end of the day forces designers to take into consideration of reducing the solar gains, or in general the internal also solar and external and internal gains. Now moving to the second methodology, this is the passive house overheating calculation. So the Belgian passive house standard is quasi-dynamic calculation. It's also based on the PMV PPD method of the EN 15251. And for certification purposes, in Belgium, the limit of the overheating hours exceeding the 25 Celsius threshold is 5 degrees. If we compare this with the German PHPP, it's 10%. So in Belgium, we are tolerating less the exceedance of overheating degrees. So this was the second methodology that we are using. We are talking here about operative temperature versus humidity. And then finally, the third methodology that we opted to use, it's a methodology based on Hamdy's work. And in this approach, you can see that there is a need at least for 3 or 4 4 actually future weather files, including historical weather file, a mid-century and end of the century weather file. And luckily, as part of the occupant project that we are working on, one of our colleagues, Xavier Vetweis and Sébastien Deltroupe in the University of Liège, they already developed their own MAR model, and this MAR model is based on the new IPCC 6 report, assessment report, where we have the worst scenarios of the SSP5, 2.6, 3.7, and 4.5, and 6. And our MAR model that is developed at Liège University has a 5-kilometer horizontal resolution and daily output. From there, based on in compliance with ISO 15927, we generated the TMOIs, the XMOIs, and the EPW formats in order to run the simulation. Furthermore, just to give you some idea about the IED overheating degree indicator, it's an indicator introduced so that different thermal comfort limits for different zones of a dwelling can be considered, take into account the particular occupant's behavior and the adaptation opportunity in each identified zone, so it can distinguish sleeping room, circulation, living area, and so on. And it accounts for both the intensity and the frequency of the indoor overheating. The intensity is quantified by the temperature difference and between the free running indoor operative temperature and a chosen thermal comfort temperature limit. Whereas the frequency is calculated by integrating the intensity of the overheating during the occupied period into the different building zones to present the overall overheating in a building. Next to the indoor overheating degree, we are using the ambient warmness degree, and in this sense we fixed it on 18. It could be lower, but in our case here we had it 18, and the ambient warmness degree evaluates the sensitivity of the outdoor warmness by averaging the cooling degree hours calculated for a base temperature of 18 Celsius during the summer hours when the outdoor air temperature is not lower than 18. And in this case we opted for 18. We might have opted for a lower temperature because a passive house is highly insulated. It could be 16. But this was one thing we did 1 year ago. Now we have more wisdom about this parameter that varies the result or influences the results significantly. Well, I would like now to move to the results section, and we are here literally comparing apples with bananas. So don't take this graph as a reference graph. Why is that? Because on the left side we can see the passive house estimation, which is in hours. So we are talking here about the annual condition, 400 hours exceeding the comfort range. The second 2 bars are talking here about the EPBD method. So this is this is the EPBD method, 430, but these are not hours, these are Kelvin hours, so we cannot compare. And then the third approach is simply hours of exceedance of temperatures according to the method of Hamdy in a sleeping room. So we cannot compare. The first method is a single zone, quasi-dynamic, the second the same, while the third method is a multi-zonal dynamic simulation, high-resolution simulation with different future scenarios embedded in the calculation. But still, we opted to put it on the same graph because from a point of view of an occupant, overheating is overheating. It's the same phenomena. Now, if we complexify it and represent it in Kelvin hours or in hours or whatever indicator or metric we choose, at the end of the day, it's the same phenomena. And that's the message that we want to look at, that overheating is a phenomena and it's not universally standardized, and there's a huge discrepancy between those 3 methods. Well, when we look at the differences also, we have results that confirm 216 difference in the overheated hours between the EPBD and the method of Hamdy. Yes, I got the message, thank you. And when we look at the nearly zero energy timber building, they are not able to suppress this increase in average outdoor temperature in future climate in Belgium. So this is the conclusion. We cannot, with this type of building, suppress the overheating risk. Some points for the discussion. The study is about the accuracy and the variance of 3 different overheating calculation methods, and it's underlining the critical issues and the strengths of them, of each of them. Therefore, I invite you to have a look at the paper and read it. The comparison cannot be accepted from a scientific point of view. The three methods have different purposes, which seems not to be comparable. And as I mentioned, each of the indicator has a different approach. And how far is this selected case study that we selected as a timber construction representative for Belgium? Today's Belgium stock, the existing one, is brick. So it is not representative, but it might be representative for future construction. Further points, the methodology Hamdy takes into account long-term climate change sensitive indicators and allows for a multi-zonal modeling distinguishing sleeping and living spaces. And the overheating calculation methods are not sensitive enough to solar radiation and local conditions such as urban heat effect. All three of the methods are still not addressing in accuracy or in detail the solar radiation. Yesterday, Ramin Rahif presented his paper, and he mentioned that we compared, using the methodology of Hamdy, different cities with different solar radiation but same profiles of temperature, and we figured out that there's a huge difference just because of the change of solar radiation. So in this sense, there is a need to have a hybrid thermal comfort model also to be integrated in the Belgian context, because so far we are only relying on a PMV PPD model. It might be interesting to see what neighboring countries are doing. Conclusion, nearly zero energy timber buildings are not able to suppress the increased average outdoor temperature in future climate. There is a need to improve our current legislation framework of the Walloon region in the south of Belgium. I cannot talk in the name of Flanders. By adopting the set of long-term thermal discomfort indicator that allows the classification of the building regarding future prediction and allow to check the resilience. And there is a necessity to adapt the dynamic calculation instead of the static, because when you look at our neighbor country, the Netherlands, they have a dynamic approach. The United Kingdom has a dynamic approach, and it would be interesting to look at that. Just some future, we are looking at publishing our MAR future weather data set for Belgium. We have a comparison of the overheating methods across Europe running in the IEA work. The European Commission proposal for recasting EPBD will be published end of the year or early 2022. It will be interesting what kind of a proposal will come and how the carbon emission will influence that. So we were looking to propose a new European overheating calculation method that can be unified, and proposing a new definition for heat waves in the Belgian context, not based on the Royal Meteorological Climatic Institution of Belgium and the federal government or the Federal Ministry of Health in Belgium. By that, I would like to invite you to have a look at the paper. You can find it in the proceeding, and also have a look at our website on our occupant. There's also several publications related to our work in the annex or in the project. Thank you very much for your attention.